Hello everyone. This is part 2 of section 2.3, and just to summarize, we're going to start looking at initial value problems. So finally we're at a point where we can solve certain types of differential equations by our three theorems. And remember that there are three theorems. Just to summarize quickly, I got a piece of scrap paper here. If we have real distinct roots, the part of the general solution is c1 e to the r1x plus c2 e to the r2x all the way out to as many as you have c sub n e to the r sub nx. So that was our first theorem. Our second theorem was for repeated roots. So I just want to summarize these before we go on. And the part of the general solution was c1 plus c2x plus c sub k e to the k, or times x to the k minus 1th power. Times e to the rx, where r is the common root. That's repeated with a multiplicity of k. And then we had complex conjugates. And they are of the form a plus or minus bi, and it was e to the ax times c1 cosine bx plus c2 sine of bx. So those are the three roots for homogeneous nth order differential equations with constant coefficients. So on to initial value problems. We start with the characteristic equations. It's basically just doing what we did earlier, finding a general solution, then using the initial conditions to find the particular solution. So we start with the characteristic equation, r squared minus 5r plus 6 equaling 0 in this case. This one factors neatly, r minus 3, r minus 2, or vice versa. Set each factor to 0. So we get r equals 3 and r equals 2. And so then a general solution is of the form y equaling, okay, they're real distinct roots, so c1 e to the 3x plus c2 e to the 2x. And again, if you had these reversed, and you said c1 e to the 2x plus c2 e to the 3x, the mechanics will work, of the mathematics will work itself out, so no need to worry. And so we're going to need to use the initial conditions, which include, because it's second order, includes a first derivative. So let me take the first derivative down here, and then we'll move up here for the initial conditions. So the derivative of c1 e to the 3x is 3c1 e to the 3x, and then plus the derivative of c2 e to the 2x is 2c2 e to the 2x. Alright, I'll move up here for the initial conditions, and we have y of 0 equaling 1, giving us 1 is equal to c1 plus c2, because we're substituting into y here, and y is 1 when x is 0. Obviously this e to the 0's go to 0, and then y prime of 0 was given to be 5, so then we have that 5 is equal to looks like 3c1 plus 2c2. Okay, so then we need to solve that system of two equations in two unknowns, and you can solve it any way you like. I'm going to multiply the top one by a negative 2 to get rid of the c2, and so then we get negative 2 equals negative 2c1 minus 2c2, rolling up the 5 equaling 3c1 plus 2c2, and adding together we get that c1 is 3. And then we back substitute to find c2, and I'll use the simplest equation, 1 equals c1 plus c2. So substituting c1 is 3, we have 1 equals 3 plus c2, and then c2 is a negative 2. So then that gives us our particular solution. Y is c1, which is 3, e to the 3x, and then plus c2, which is a negative 2 e to the 2x. Okay, so a couple more to look at in terms of these initial value problems. And so once again we start with the characteristic equation. So here we have r squared minus 4r plus 13 is 0. And you could try as hard as you want, but that's not factorable. So we're going to need our quadratic formula. So r is going to be minus b, so minus 4, plus or minus square root b squared, so negative 4 squared, minus 4 times a, which is 1, times c, which is 13. And that's all over 2 times a, which is 1. So we have r equaling 4, positive 4 plus or minus square root of, okay, that's 16 minus 52 is negative 36. And that's all over 2. So then we get 4 plus or minus 6i over 2. And remember, we want to put this in a plus or minus bi form. So divide the 2 into the 4, we get 2 plus or minus, divide the 2 into the 6i, we get 3i. So then from our theorem, we have that a general solution would be e to the ax, so e to the 2x, and then times the quantity, c1 cosine bx, b is 3, so the c1 cosine 3x plus c2 sine of 3x. Alright, and once again, we're going to need two derivatives, or excuse me, just one derivative to be able to use the initial conditions. And so this is going to involve the product rule. So we'll have the first factor, e to the 2x, derivative of the second, derivative of cosine minus sine. Don't forget the derivative of the argument, 3x, which is 3, so minus 3c1 sine of 3x, and then plus derivative of sine is cosine, again another factor of 3, so 3c2 cosine 3x, and then plus the second factor, so what's in parentheses, derivative of the first, and the derivative of e to the 2x is 2, e to the 2x, so I'll write that, and then what's in parentheses, unchanged. Okay, and there's really no need to simplify things. I think we can go right for the initial conditions, and things will unfold neatly. First initial condition, y of 0 was 4, gives us that 4 is equal to, okay, remember cosine of 0 is 1, sine of 0 is 0, so immediately when x is 0, e to the 2 times 0 or e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, so immediately we get C1. So that's kind of nice. And then the second initial condition, y prime of 0 was 14, gives us that 14 is equal to, okay, all the e's to the zeros are 1s, and again sines go away, cosines stay, because sine of 0 is 0. Okay, so this cosine of 0 is 1, so the 3c2 stays. And then here, this c1 stays, but don't forget, and this sign goes away, but don't forget this 2 out in front. So 4c2 plus 2c1. Okay, and then basically we just back substitute, because c1 was 4. So 14 equals 3c2 plus 2 times 4. And that gives us, so this is 8. 14 minus 8 is 6, equals 3c2. So c2 is 2. Okay, so then to our particular solution, y would be the e to the 2x, and then times c1, which is 4, cosine 3x, plus c2, which is 2, sine of 3x. Okay, so then we have one more, and this is a third order homogeneous linear differential equation with constant coefficients. But we start the same way as always, characteristic equation first. So 2r cubed minus 3r squared minus 2 is 0. And, I'm sorry, minus 2r, that's a y prime. And we first factor out an r, so then we have 2r squared minus 3r minus 2 equaling 0. And that quadratic actually factors. We have a 2r and an r, and let's see, if we put a 2 with the r, make it negative, and a 1 with the 2r, and make it positive. That's the correct factorization. So set each factor to 0, so r is 0, 2r plus 1 is 0, r minus 2 is 0, so r is 0 is a root, negative 1/2, and 2. Okay, so 3 real distinct roots. So then a general solution is y equaling, okay, I'll say c1, just to be explicit, c1 e to the 0x plus c2 e to the negative 1/2 x plus c3 e to the 2x. But of course we're not going to keep e to the 0x, so that's just c1 plus c2 e to the negative 1/2 x plus c3 e to the 2x. And at this point we're going to need two derivatives because it's a third order and there's 3 initial conditions up to and including the second derivative. So we'll need 2 derivatives, so y prime, well the derivative of c1, that's a constant, so that's 0. Here we get the derivative of e to the negative 1/2 x, which is negative 1/2 e to the negative 1/2 x. So we have negative 1/2 c2 e to the negative 1/2 x. and then plus the derivative of c3 e to the 2x is 2 c3 e to the 2x. And we'll need one more derivative, y double prime. And basically the first term, the other factor, negative 1/2, gives us 1/4 c2 e to the negative 1/2 x. And for the second term, another factor of 2 gives us plus 4 c3 e to the 2x. Okay, so now let's use the initial conditions. And so the first initial condition was y of 0 was 1. So that gives us, going back to y here, c1 plus c2, that 1 is equal to c1 plus c2 plus c3. Second initial condition, y prime of 0 is negative 1. And so we have negative 1 equals, into y prime, negative 1/2 c2 plus 2c3, and y double prime of 0 is 3. That's our final initial condition there. Gives us that 3 is equal to negative 1/4, or I'm sorry, positive 1/4. C2 and plus 4c3. Okay, so there's a system of 3 equations in 3 unknowns, and I think the most advantageous thing to do here immediately is to get rid of the fractions in this second and third equation by multiplying by the least common denominator, which for the second equation is 2 and for the third equation is 4. So let me now move all of this up here, and I'm not going to forget the fact that the first equation was 1 equaling c1 plus c2 plus c3. Multiplying a 2 by the second equation, we get negative 2 equals negative c2 plus 4c3. And multiplying a 4 by the third equation, we get 12 equals c2 plus 16 c3. Alright, so then if we take these bottom two equations, negative 2 equals negative c2 plus 4c3, and 12 equals c2 plus 16c3, we just simply add them together, and the c2s are eliminated. And that gives us 10 equals 20c3, so c3 is 10 over 20, or 1/2. Okay, and then back substitute into either one of those. I'm going to use the negative 2 equals negative c2 plus 4c3 equation, and replace c3 by the 1/2. So negative 2 equals negative c2 plus 4 times 1/2. So that's negative 2 equals negative c2 plus 2. So that would make it negative 4, but then multiplying by the negative, c2 would be positive 4. And then go back to the first equation containing all 3 of the constants, and replace c2 by 4 and c3 by 1/2. So then we get 1 equals C1 plus 9 halves. So C1 would be negative 7 halves. And so now we could write our particular solution, and that is y is, okay, so it was C1 negative 7 halves plus C2 e to the negative 1 half x, so we're up here at y, so C2 was 4, so plus 4 e to the negative 1 half x, and then plus C3, which was 1 half, times e to the 2x. Okay, so now we have one more concept remaining for this section, and basically it's involving higher order differential equations, but a situation where one solution is given. And as I noted here, if we know one solution, then we know, and this at least, you'll see what I mean by that in the second example, but you know at least one of the roots of the characteristic equation. So in these examples, it says one solution is given, find a general solution. So the fact that, let's do it this way, since y equals e to the that's a 2/3 there, e to the 2/3 section x is a solution, this implies that r equals 2/3 is a root. And if it's a root of the characteristic equation, and if it is, then it's going to cause a 0 when we perform, notice that this is third order, right? And the characteristic equation is 3r cubed minus 2r squared plus 12r minus 8 equaling 0. So the nice thing is, instead of having to do the p's and the q's for the rational root theorem like we saw earlier, we could just use 2/3 and we know it's a root. So I'm going to do it right here. We'll set up, peel off the coefficients, 3, negative 2, 12, and negative 8. I'll put my root, little box to the left, space for some entries, my addition bar, bring down the 3 times the 2/3, so 2/3 times 3 is 2, gives me 0 here, 2/3 times 0 is 0, get 12, and 2/3 times 12, 3 goes into 12, 4 times 2 is 8, and as we would expect, because we're told we know 2/3 is a root, we get a 0 here. So now we know that r equals 2/3 is a root, so then r minus 2/3 is a factor. So here we would have r minus 2/3 and then times the quantity, this is a third degree. We depressed it to a second degree, so that would be 3r squared plus 0r plus 12, or just 3r squared plus 12 equaling 0. Okay, and so at that point we can, actually this is a sum here. You could factor out a 3 and then divide by it, but I think I'll just leave that as it is, and since it's a sum of two squares, I'm going to set everything to 0. So r equals 2/3 we know is a root. But then here I'll solve for r by isolating the r squared. So 3r squared is 12, r squared would be -4, r is plus or minus the square root of -4, or plus or minus 2i, which if you like, 0 plus or minus 2i, so that you could show the a plus or minus bi form for the complex conjugate root. Okay, so now we know a general solution then is y equaling, okay, the c1 e to the 2/3 x coming from the 2/3, but then coming from the complex conjugate pair, plus e to the ax, so that's e to the 0x, and then we'll say c2 cosine, b is 2, so 2x, and then c3 sine of 2x. And we don't want to leave the e to the 0x here, so just c1 e to the 2/3 x plus, that's 1, so just c2 cosine 2x plus c3 sine of 2x. Okay, and then a final example, and this is what I meant by the comment of at least one of the roots in the little note there, is because if this term is a solution, e to the -x sine of x, so since y equals e to the -x sine of x is a solution, we know that a is -1 and b is 1, imply that -1 plus I, let's say r equaling -1 plus I is a root. Okay, so we're going to start with synthetic division. First off, the characteristic equation is 9r cubed plus 11r squared plus 4r minus 14 is 0. And we'll start this with synthetic division by peeling off the coefficients 9, 11, 4, and -14. Leave a space for some entries, my addition bar, and the root in the upper left, which is -1 plus I. Okay, so now we have to just be a little bit careful. We'll first bring down the 9, and then we're going to multiply. So there, I'm going to do this work aside. 9 times -1 plus I is just -9 plus 9i. So then 11 minus 9 is 2, so we get 2 plus 9i. And now we've got to multiply the -1 plus I times the 2 plus 9i. Okay, so we're taking this entry times the 2 plus 9i. So we get -2 minus 9i plus 2i plus 9i squared. Oops, I'm sorry. I don't think you were seeing that. Okay, so give me time to catch up there. But the I squared is negative 1. So that would give minus 2. This would be plus 9 times negative 1 is negative 9. So minus 2 minus 9 is negative 11. And then the negative 9i plus 2i is negative 7i. So here we get negative 11 minus 7i, which when we add, we get negative 7 minus 7i. So now we've got to take the minus 1 plus I and multiply it by the 7 minus 7i. Because again, it's this entry here, the minus 1 plus I times the minus 7 minus 7i. And foiling that out, minus 7 plus 7i, plus 7i, minus 7 plus 7i, plus 7i, we should get a cancellation here. I'm sorry, something's going wrong. Oh, that was a negative 7 minus 7i. That's my mistake. I miscopied this. So that was a negative 7. I knew something was going wrong there. Okay, so let me start that over again. Okay, so we get positive 7 plus 7i, and then the inners is minus 7i, and then we get minus 7i squared. Okay. And then the I squared is a negative 1 again. The i's are gone. 7 minus 7 times minus 1 is positive 7. And as expected, we get a 14. And I say as expected because we knew that minus 1 plus I was a 0, or a root. And so therefore, of course, it's going to give us a 0 when we do our synthetic division. Now the thing is, at this point, this is a third order. So this is second order. But I'm not going to write 9r squared and then plus 2 plus 9i times r, and then plus this minus 7 minus 7i as its constant. Because I know that these complex roots, so we'll say since complex roots occur in conjugate pairs, we also know that r equals minus 1 minus I is also a root. Because we had minus 1 plus I, but then the complex conjugate is minus 1 minus I. So from this point, this would be the most advantageous thing to do. Just use that root, minus 1 minus I, and continue with synthetic division. So bring down the 9. We'll do this work aside again. So it's minus 1. So it's 9 times minus 1 minus I, minus 9 minus 9i. So minus 9 minus 9i. You know how neatly that works out. The 9's and i's go away, get minus 7, and then we have the minus 7 times the minus 1 minus I, which gives us 7 plus 7i, and the 7 plus 7i gives us another 0 as we expected. So now, this is second degree. We depressed it again, so this is first degree. And I'm not going to bother listing the factors. You could if you wanted to. But this is basically saying that the remaining factor is 9r minus 7. That we'll set equal to 0. So therefore, r is 7/9 is also a root. So our general solution would be y equals c1 e to the 7/9 x, and then plus from that complex conjugate pair e to the negative 1x, or just e to the negative x, and then c1 cosine x plus c2 sine of x. Okay, so that's a classic problem. I like that example. And you'll probably see something like that on the exam. So that's the end of section 2.3. And we'll see you when you're ready for 2.4.